Hi everyone. Um, Good evening and welcome to this week's live session. So I believe all of you would have gone through this week's lectures, and I believe we are getting into the business end of the course, where you are coming to you're getting introduced to the latest, or rather the cutting edge technologies that we have in the world of networks, right? And basically, you're being introduced to something called programmable networks. And as usual, I'm Harish, and I'm a PhD scholar at IIT Hyderabad. And if you have been watching any of my previous lectures, you would know that I always start with looking at the questions that we are to tackle today, and we take it forward from there. Where we identify some keywords and we take a look at um, uh, how we can understand what is being told in the lectures, right? So the objective of these classes are to solve previous year questions. That is always one, but the bigger objective that I feel that I should do as my responsibility is to explain the concepts in a way that someone who is not familiar with network backgrounds also understands, right? Although of course you are expected to know basics of computer networks, you take advanced computer networking. But but for those who are interested in ACN but do not have the time to go through the network's basics, so I'll try to explain the concepts in a very simple way. I'll try, of course. And if you have any questions, you can ask me. We can wait for another 5 more minutes for people to join, and then let's get started. Okay. Okay. So this week, I believe you would have been introduced to something called the data plane, not just the data plane. So we looked at data plane last week. This week would have been data plane programmability. So I'll bust the myth over here. So last week we learned data planes, right? So data planes are part of the forwarding hardware, right? And You can program it. Those data planes are called programmable data planes. It's as simple as that. There is no other aspect to this. It's just a data plane which is programmable. So why we need this programmable data plane and what is the motivation behind programmable data planes? Let us look at throughout the course of this lecture. And also you would have learned something called P4 in this lecture, right? So what is this? We'll look at that. And this time we're only going to look at 3 questions. So the first one is how many header match fields are defined by OpenFlow 1.3? So what is this OpenFlow? What is its relationship with P4? And what is its relationship with programmable data planes, PDPs? PDP means programmable data planes, right? Let's take a look in the future. Basically, how many header match fields are defined by this OpenFlow 1.3? Okay. And that is it 12 fields, or is it 36 fields, 40 fields, or is it 44 fields? And the next is, which of the following statements are correct about the P4 language? Once again, we're getting this thing called P4. So what is this P4? Why do we need P4? Could we already have C, C++, etc. Right? So what is the need for the P4? We'll look at that. And right, so what are the correct statements here? So P4 is a domain-specific language for programming input devices. P4 is primarily used for programming the control plane of network devices. P4 is case-insensitive language. P4 is a statically typed language. P4 is a protocol-dependent language, right? So let's see. And which of the abstractions does P4 support? So is it protocol independence? Is it compile independence? Is it target independence? Or is it processing chain independence? But while we try to answer these questions, we'll also understand the history of why programmable data planes came, and we'll go forward from there. Okay. For this, I will talk a little bit about SDN once again, and from SDN we will move towards then the shortcomings there, and then moving towards PDPs. Yeah. Sorry, this diagram is not that intuitive. Okay, so we'll move on to so this is ACN week 8. So we saw some keywords like this: blue, programmable data planes, P4. This we saw multiple times. All right. So what are these? let's begin this with small introduction on SDN. Okay. Right. So let's start with what was explained in the first lecture. So around 2010 to 2000, let's say now. So people started coming up with new paradigms like SDN, right? And then we also learned something called NFV, network function virtualization. Right? So around 2010 or this time or before that is when they started looking into concepts like, can we completely have a clean slate implementation of the internet? Can we completely tear things down and rebuild it from scratch to make the internet more robust? Although that is not what happened. And this around this time is when something called open flow also came up. Okay? And around 2014 is the seminal paper that came up, which is about P4. So P4 was the language, but this was a bit of a landmark paper in the sense that it gave rise to programmable hardware that was actually realizable, that has actually even been realized in in, uh, in, in actuality. It's P4 led this started a large movement. And before P4, there was also something called RMT, configurable matching tables. So let's not worry about that. We'll only look at P4 there. And till 2021, 2020, let's say I think Tofino came out at this point of time. Tofino switch 2017, I believe. I'm not sure. Let me find out. Okay, so the Tofino switch came out, which was programmable using this P4 language. And here we are, where we have SmartNICs and CPUs and switches and switches which support P4. All of these things support P4. So what is this P4? Right, so what is P4 and why is it taking over the world of networking by storm? Okay, so but before that, we shall take a look at SDN. Right, so this is just another recap of what has happened so far this lecture. This lecture series, that is. So SDN, what did SDN do? SDN made a clear abstraction between the control plane and the data plane. Right? And here you have control plane and then you have the data. So the representative diagram for this is you have 4 switches, let's say. And all these switches have control plane and data. Control plane, data. Control plane, data plane. Control plane, data. Right. So all these switches have control plane and data plane embedded into them. And this was the traditional networking. But in the paradigm of SDN, the control plane was centralized, and the control plane could interact with the data plane. So from a layman's point of view, we can say that controlling the data plane was centralized. It was abstracted. So there is a computer that sits somewhere, and that computer is going to give instructions to the switches as to what to forward, where, when, and how, right? And this system that we call is sitting in the control plane, of course. So this was the change, the paradigm change that spurred a lot of innovation. Right? But the story is not over yet. So there is SDN, is software defined network. Software defined networking, right? Right. So, so from software defined networking, we are seeing a new paradigm called programmable data planes. So from the name itself, programmable data planes, you can have some idea that, okay, so this is the data plane here. So, yeah, right. So we're seeing a new paradigm called programmable data planes, right? And imagine if this data plane was programmable. No, but why would we need to program it? Correct. So there is no need to program this at all. And because the data plane, what does it do? Data plane does simple tasks like forwarding, meaning whatever packet comes into the input port, it does some operations on it, and those operations mainly are matching. It takes some of the header fields from the packet, matches here, then puts it on the appropriate output for this forwarding. So who fills this table, or rather who gives the logic for the matching, or the entries for the matching? Mostly the control plane. The control plane has its own um, control plane has its own um, logic that it has its own view of the topology of the network, and it tends to compute the best forwarding directions for each of these switches in order to maximize the throughput in the network. The control plane tends to do those aspects, and finally it sends the results onto the data plane, which then executes these actions, right? In reality. So that's what that's what happens. So what happens here? The problem here is control plane is sitting somewhere far away. Let's assume. As far away, it is in the order of milliseconds. TP is order of milliseconds. Data plane is in the order of only seconds. Sorry, it's in the order of nanoseconds. So there is a big difference in the time, right? So imagine a scenario where um, you have to take the switch to take decision based on the input packet header. This is a hypothetical scenario. So consider that there is a switch. It has two ports over here. Depending upon the values in this header, it needs to send it either to here or there. Right. And based on this header value, some processing is required. Okay? It's not straightforward as matching. So what tends to happen here is the packet comes here, and then the switch does not have a match. So this is sent to the control plane. The packet is sent to the control plane. Control plane analyzes it, and it sends the response back to the switch saying forwarded on to this interface. Right? Now, the time that this packet has spent inside the switch comes to be in the order of milliseconds. Why? Because copy of the packet was sent to the control plane, and a response was received once again to the switch from the control plane. So the control plane processing is in the order of milliseconds, and probably the communication delay will also add on to these milliseconds. Right? So probably it will be in the order of seconds also. We don't know. Right? So right after the right, so it must be in the order of seconds as well. But the data plane is capable of forwarding packets in the order of nanoseconds. So naturally, the question that is being asked is, why is it that we have to do everything at the control? Question is, why should we do everything at the control plane itself? Second question, can we offload some control plane logic to the data plane? The answer is yes. It's a big fat yes. And what happens when you offload some control plane logic to the data plane? to give rise to programmable data planes. Okay, so this is basically what programmable data planes are. You add some flexibility to the data plane itself, where it can recognize multiple header fields, and it can do so at the nanosecond time scale. So that's the most important part. That's that's very crucial. Right? So you don't have to wait the response from the control. Um, so in this context, this is called as the slow path because it takes time. And this is the fast path. So now we have some idea about what why we need programmable data planes. Let's just talk a little bit about um, the state of the networking industry before SDN. Before SDN, right? So as you know, the world of networking is constantly evolving, right? Which means new header fields are added. Correct. So when these new header fields are added, we have a problem now. So why are these header fields added? It is to either serve a new protocol, and this protocol might be making things faster. Faster or more efficient. Right? So one example for a new protocol, or rather something like explicit congestion notification, ECN. We have some header fields that tend to inform uh, the network about how it should behave. Right? These are all new ideas that came up, and in this case, they were able to accommodate it in existing space of the header fields. But this might not be the case all the time. So the case may be that you have to add a completely new header, a completely new header field has to be added, and so on. Right. So this is basically to support innovation in networking. Okay. Now let's assume that a new header field was added. Added, and next problem arrives. Will my network hardware support new header field? Right? So by that, what I mean is these switches are all high-speed networking devices in such a way that you have the ASIC in it, correct? So ASIC is application specific integrated circuits. It's application specific integrated circuits. And or rather you can call it as nothing but application specific chips. Like chips, right? So not one is a wheat, of course. Okay. So the whole point of application specific is to cater to a particular application, and in this case, cater to the application of networking. So networking, what is this? What is the primary thing that this chip has to do? It has to match header fields. So it has to match header fields. Right. So what are all the list of header fields that it will match? Let us say this specific integrated circuit is designed to match with 30 header fields. Now I am adding 31st header field. 31st is the new header field that I'm adding. So will this be will this be possible on the existing fixed function ASIC? No, because these ASICs are fixed function, right? So by fixed function, you don't have a lot of flexibility. You don't have a lot of flexibility in reconfiguring it. So therefore, my new concept cannot be implemented on real networks. Right? So this might seem small, but for the evolution of networks, this is a very, very important aspect. If you cannot test it, then how will we know its performance, right? Test or evaluate it, right? So so what happened here was there was a need to be able to reconfigure reconfigure this ASIC in such a way that you're able to recognize new header fields. All right. So this is also one more motivation for the emergence of programmable data planes. Right? So if in one diagram we have to uh, explain what this is a situation. So basically, you have the fixed function switch. Now the switch OS. And the switch OS basically says this is how I process packets. There is no changing the way in which I process packets, right? So let's take a deeper look. This gives us the motivation to look at how these packet processing happens. Okay, so how does the packet processing happen? So what are the components of it? So if you look at it like this, imagine if there is the switch. There is the switch. So you have packets that are coming in this direction and packets are going out this direction. All right. So the first component is basically a parser. And this parser is fixed. We'll look at what these things do. And there is something called a pipeline. So what is a pipeline? So this is called as a header processing pipeline. So a pipeline is nothing but a connected set of tables. Okay? So the first table, let us say, is an L2 table. Second table, let us say, is IPv4 table. Third table, let us say, is IPv6 table. The fourth table, let us say, is ACL table. ACL is access control lists. So that's slightly beyond the scope, but imagine if that there is a need for an ACL, access control list. Oh, right. I think we did study about access control lists, right? The previous lecture. So I think, yeah, we should know what access control lists are at this point in time. So This is all in a fixed function switch, fixed function ASIC. Okay. Now, associated with each table and each entry is also an action. Action here, action here, action here, action here. Right. That's the deparser. Let's not worry about that right now. So essentially, if you look at how the header matching happens inside the switch, it happens such that the packet passes through each of these pipelines. Okay. Now let's assume the packet is entering the switch. So what will the parser do? The parser is given, is provided the logic. Okay. This logic looks like a state machine. State machine, what I mean is if something is a match, then you go to the state, and if this is not a match, then you go to the state, right? And if something is a different match, then you go to this state, and if not, then you go to this state, and then you match the next packet, right? So basically what this means is if the packet is, let's say, IPv4, then please go to the state and match the next set of header fields which correspond to IPv4, right? If it is not IPv4, if it is, let's say, okay, I think the best example is TCP. If it is TCP, then you go and look for TCP specific header fields in the next state. But if it is UDP, it doesn't make sense to look for TCP specific header fields, right? Because it is not going to have any of those header fields, right? TCP has a lot of flags which help it communicate, perform three-way handshake. None of that is available. None of that is needed for UDP. So basically, what this state does is it goes through this state machine. I mean, it possibly that is programmed by someone else. It's programmed by someone else, and it is put inside the hardware. Now, if I want to add a new state here for a new kind of header field, I cannot add a new pointer from there to here because this is highly integrated with the circuitry. And why is it integrated? It is integrated in order to maintain line rate speeds, right? So we cannot open it up to programming without losing speed that easily. So that's why this is called fixed function, right? So now the parser is done. Now we have parsed it, and now after parsing, the switch will have all the relevant header fields in its memory. Or in other words, the switch goes through the packet top to bottom and keeps the values of all of these header fields that it was that it could recognize, right? And it keeps it in its buffer. So some of these header fields could be L2, some of them could be IPv4, some of these could be IPv6, some of these could be ACL, right? So now it has the header fields in its hand. table, IPv6 table, and then it has an action 1, action 2, action 2, action 2. So it takes the relevant L2 header and then it checks the table one by one. Oh, not one by one. If it has specialized hardware, then it can do it parallelly also. But just for simplicity's sake, it takes the L2 header fields, MAC address, and it checks: is it a match? 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 So whichever table entry here has a match has an action associated with it. So an example of an action could be could be drop the packet, or it could also be um, uh, to forward the packet to the next through a particular port, right? So depending upon that, and if there is no match, maybe it will send it to the IPv4 table. Right? And the logic of which table has to be matched first, second, third is also hard coded. The logic is also hard coded. Give me 1 second. Right. So the logic is hard coded. The logic is hard coded. Which logic is hard coded? The logic of where the packet will go and how will it match. So they would have said, okay, first go and match to L2 table. And after that matching, you go and match to the IPv4 table, and so and so. We do not match with the IPv6 table if you don't find the IPv6 mark. Okay. So this is the problem. You cannot configure the way in which the match action pipeline match action pipeline. Configured. Right. So this is the problem with fixed function exits. So now this is the entry for protocol independent switch architecture, or PISA. So in a summary sentence, the programmable parser that is defined, um, uh, it, so the parser, right? So this parser part, it's spoke about here. Parser is programmable. So this might seem like a very small change, but it has a huge impact. So that is, if I'm building a custom header, then I can program the parser to identify that custom header and possibly take decisions based on that custom header. Right? So because now I can program the parser and see the state that I wanted to add before, I can add it along with the existing states. So along with this, if you also want to dictate um, which actions I want to take, and depending upon which particular sort of headers that I encounter, uh, that means I also want to dictate which are all the match action pipelines I want the programmable match action pipelines that I want the switch to do. So that might mean that I may want to do the layer 2 header match or the layer 2 actions to be taken. I may want to do layer 3 and layer 2.5 also, or layer 4 or encapsulation, or all the aspects we would want to put it in. So how would it how would we do this particular aspect? Right? And that is where we need a programming language. Correct? We need a programming language, and we also want a compiler that compiles language and puts it on the PISA. PISA is nothing but protocol dependent switch are key architecture. So what will be the advantages of this? So one thing is it could reduce the complexity And second is it can allow addition of new features to the network, and it also has telemetry capabilities, meaning we can uh, create our own header fields and piggyback metadata about packets or flows on top of these packets themselves, right, without sacrifice. Right? And P4 was what gave us this in a solid way. Okay, now it is time for us to move into something called OpenFlow. Okay. So we had already studied what OpenFlow is. So what is OpenFlow? It is a defined method or a protocol, basically a protocol that enables control plane, data plane interaction in a standardized, right? So we studied that there are some fixed types of messages. For example, update, right? So this tends to update the flow entries in the table, right? And etc. So what are the advantages of this? This made networks easier to manage, also gave centralized control, and also allowed code reuse. Right. So what we have to understand here is OpenFlow did not fundamentally change the core network functionality, meaning it did not make any changes in terms of how the packets would be processed in the data plane, still remained largely unconfigurable. But it did solicit the requirement of open flow compatible switches. Right? It did bring up something called open flow compatible hardware, meaning those switches which understands the open flow protocol and the messages, right? For example, a switch that understands. So essentially, uh, what it did was it just made the control plane a bit more programmable. That's all. That's all that it did. So why was it made a bit more programmable? Now, because everyone had a common set of APIs. APIs to interact with the data plane. So CP programmability was brought on a common platform. It was brought on a common platform. So people could program it, and irrespective of say manufacture or make the switch. But what was the caveat with OpenFlow? Funnily enough, the OpenFlow compatible switches still supported only a fixed set of header fields. Right? So this OpenFlow specification went through multiple iterations, and OpenFlow 1.0 could only match 12 header fields. And it only supported 12 kinds of header fields. And OpenFlow 1.4, it went to 40 header fields. And So 0.5 is at 44 header fields, meaning the APIs will give you the ability to match using any of these already defined header fields, but it does not give you the ability to add new header fields. Okay. So once again, the problem persisted. How can we leverage, or rather, how can we extract? How can we leverage data plane better? So one aspect is you need to be able to define your own parser. The parser is what extracts the header fields. So this is precisely what we saw, and these new header fields could possibly be, there is, you might have some new needs, some new encapsulation formats or different protocol versions, additional measurement related headers. These are all new things that were added, right? So some specific, this is, once again, I'm just relaying this information from your lecture. The specifics are that what are the benefits of data plane programmability. So one of the major benefits is there is flexible parsing. Matching on non-standard fields and spurs network evolution. It spurs network evolution is usually a new protocol, a new header field, let's say. Takes 4 to 5 years. Why? Because of the requirement of hardware upgrades. So one question that might pop up is, right, all these benefits, what are we losing? So because there are no free lunches, right? Where an elaborate version of this question is, how do we know if programmable switch chip has the same power or performance and cost as a fixed function chip? Well, how do we know? Through statistics, and happily enough, uh, the statistics that were shown in the lecture says that this P4 based Tofino. This Tofino is nothing but a switch chip which enables data plane programmability. So the throughput, and the forwarding rate are all almost in par at par with a fixed function chip. But in let's say in practice, before programmable uh, switches were not uh, did have some extra latency because they tend to use some more CPU cycles. But yeah, generally they're very comparable. Okay. So what are the limitations in programming? Programming the data plane. What are the limitations in this? All processing must maintain line rate. Second, no loops are allowed. Third is no floating point computations. Okay. And generally, this is the constraints. The reason for this no loop is because imagine if you write a loop that runs 1,000 times and then the packet is stuck inside the switch, right? So you can't give that kind of power to a programmer that has the potential to slow the switch down. So when P4 as a language, let's look at P4 as a language. Right, so what are the goals for this? First is protocol independence. Second is target independence. And third is reconfigurability. Right. So there is protocol independence, there is target independence, and there is reconfigurability. So protocol independence means the packet parser is not fixed. You can rewrite the packet parser. Right? And target independence would essentially mean that the programming language is not tied to a specific vendor hardware. In other words, it has a compiler that can compile the language or the program or the code that you've written and deploy it in multiple hardwares that run the same chip. In the case of P4, it is Tofino. So, and then reconfigurability. So you can reconfigure the way in which you do the match and action functions. You can reconfigure the logic there. And more importantly, all this has to happen. This has to happen when without system downtime. So I think at this point of time, going deep into P4, right? Okay, I'll just talk a little bit about the parser, which has been spoken so much about in today's lecture. Right? So, uh, uh, programmable parser. So let's see how the code for a parser would look like. Okay. So the P4 code for a parser starts like this: parser start is a start state, and it is Ethernet. So this Ethernet is nothing but it is a header field that is defined before. Right? So I'm defining the header field Ethernet. So the fields inside this is destination address which is having 48 bits, and source address, which is having 48 bits, and Ethernet type, which is having 16 bits. So with this header definition, right, so we can define any number of headers. Now you have basically said there is a destination. This destination MAC address is a source MAC address, and this is the other type, right? So you have defined it. Now you can use this defined header fields. Now you're defining these header fields. They're using it for parsing. Okay. So how would a parser look like? It says start, and you start parsing the Ethernet. And inside the Ethernet, right? So now go into the state called, okay, this is start state, and go into the state called Ethernet. Because I told you before that the parser is nothing but a state machine. It's a finite state machine. So parser Ethernet is, let us say, switch ether type. Case 0x8100. I'll explain what this is in just a moment. VLAN, let's say case 0x9100 VLAN. Case 0. I'm just taking the same program from your lectures. IPv4. And then you can have a number of such cases. You close it. Essentially, what this means is you're starting the parser and you are telling the parser to go into the state called Ethernet. And in the Ethernet state, what is going to happen is it is going to parse the Ethernet field, right? So because I've said Ethernet, the Ethernet field, and inside the Ethernet field or the header field, you have something called ether type. So in this ether type, it holds a 16-bit value, and that value could be something. If that value is 8100, then go into a state called VLAN, which is basically nothing but the header field defined for VLAN, and the parser also that's defined for VLAN. Similarly, if it is 9100, also you go into VLAN. Else, if it is 080x800, which is nothing but the code for IPv4, go and parse an IPv4 packet. Essentially, what this is trying to say is depending upon what is found in the lower layers, you have appropriate layers on top. So there are hints in the lower layer, like for example, ether type, the type that you expect above it. Okay, so depending upon that, you go and then you parse the fields accordingly, right? So in a way, if you want to take a look at P4 and its uh, semantics, you can go to p4.org, where you have all the tutorials set, and you have a repository called P4Lang, where you have beautiful exercises. All you have to do is download a VM, and you can start writing your own P4 programs. Right. So there are also other aspects to this, like table definitions, and actions, action definitions. Right. So these are all the aspects about table, the aspects about P4, which you could you could expect to find when you study more about P4. So in a nutshell, what is P4? What is P4? In a P4, sorry, in a nutshell, if this is the P4 switch, right? So let's go a little bit deeper. The P4 switch has match action tables, right? And it also has a logic, right? Now, as a user, I write my own P4 code and I compile it and I put it into the logic area. And what will this logic area basically say? Logic area will say process the packet so and so, in a way where first you process it by going to this first table, and then you go to the second table, and then you go to the third table. But if the value matches something else, you go to this table. So essentially you're defining the tables that that has to be matched based on the packet header values that are found in the packets, right? So that's the logic, and that's what you define. And this is done during the initialization, right? So once you put this program onto the switch, right, onto the switch, onto P4 switch. Once you put your program onto the P4 switch, next what? Now your program is written in a way where it expects certain values in the match action tables. So now you can push these rules / entries in the match action tables. And by that, you have almost all control over a data plane, the data plane device, without losing throughput and speed. Throughput and without losing a lot of throughput and a lot of latency. Right. So that's the innovation when it comes to P4. And the switch that brought it alive was called Tofino chip. Chip. And this chip is in some switches. So vendors buy these chips and they implement it in their switches. One of them is Edge Core. This is what we have in IIT Hyderabad, and this in fact gives you a lot of flexibility where you can create new applications that work completely on the data plane itself. So imagine if you can implement a decision tree based firewall matching for let's say IoT networks. And that was basically my research, and I implemented a decision tree, a multi variable decision tree, multivariate trie onto the data plane in such a way that can basically encode the rules of almost 500,000 IoT devices on one switch. So it tends to speed up a lot of these aspects about it tends to give you opportunities to speed up a lot of aspects. So essentially that is what is the selling point of P4 and programmable data planes. Now we have other target hardwares that also support P4. So what we write in P4 will get translated onto the specific hardware, and and you can just worry about programming it instead of looking at the low-level details. So this is very similar to the paradigm of C, C++, or Java. You're not worried about which hardware you're running on. Download the appropriate compiler, and then you run it, and the compiler compiles it to the specific hardware at the bottom. Right. So I think that would be enough for today. Now we'll move on to the 3 questions that we saw before. The first question was, so question number 1 is, I think I'll have to write it down. How many header match fields are defined by OpenFlow 1.3? Right. So this is basically like there are OpenFlow has it has many versions, right? So OF 1.0 and then 1.1, 1.2, 1.3, 1.4, yada yada, right? So 1.3 basically had 40 fields. We saw this in the lecture also. And 40 fields. And that is the answer. And they've asked, the second question is, which of the following are true about P4 language? Is it that P4 is a domain specific language for programming network devices? Or is it that P4 is primarily used for programming the control plane of network devices? Or is it C, P4 is a case insensitive language? Or D, P4 is statically typed language? Or is it E, P4 is protocol dependent language? So if you look at the options, let's go one by one. So P4 is a domain specific language for programming network devices. Yes, absolutely yes, right? P4 is primarily used for programming the control plane. I don't think so. It's for the data plane, so this is wrong. So P4 is a case insensitive language. No, it is a case sensitive language. This is wrong. And P4 is a statically typed language. Yes. And P4 is protocol dependent language. No, this is protocol independent language. So this is wrong. So A and D are the answers. A and D are the answers. And what are all the abstractions? what are all the abstractions that P4 supports? So the answer for this is compiler independence, right? So the idea here is it does not worry about which compiler is going to compile the code. It's just going to write programs in its own syntax, and it's not going to worry about the target in which it's going to be. Right? So I think this is what is for today. We've covered data plane programmability and in specific P4, and we also saw why P4 came into picture. And for P4 there was OpenFlow, but OpenFlow was not enough to um, cater to the innovation that was required in networks. So then came P4, which is nothing but a way to a language that programs programmable data planes. And here we are at this point of time in history where we are moving towards a programmable network infrastructure. So I'll be around for another 10 minutes, and if you have any questions, you can ask me. I'll sit very quickly. Thank you.